4.5 billion years ago, in a quiet corner of the Milky Way galaxy, something extraordinary was about to happen. A vast cloud of gas and dust, stretching across trillions of kilometers, began to collapse under its own gravity. This was the moment our solar system was born, a cosmic dance that would create 8 planets, countless moons, asteroids, and comets, all orbiting a single brilliant star we call the Sun. This is the story of our cosmic neighborhood, a tale spanning billions of years, from violent beginnings to the emergence of life itself. It's a story written in the rocks of planets, the ice of comets, and the very atoms that make up everything we see around us. Our story begins not with planets or stars, but with death. 5 billion years ago, a massive star, perhaps 10 times the mass of our Sun, reached the end of its life in a spectacular supernova explosion. This dying giant scattered heavy elements across space: carbon, oxygen, silicon, iron, and dozens of other elements forged in its nuclear furnace. These materials would become the building blocks of our solar system. The shockwave from this ancient supernova rippled through nearby clouds of hydrogen and helium, remnants from the universe's earliest days. One particular cloud, spanning roughly a light year across, began to tremble under the influence of this stellar death throes. Gravity, the weakest but most persistent of nature's forces, began to pull the cloud's particles together. As the solar nebula contracted, it began to spin faster, much like a figure skater pulling in their arms. The conservation of angular momentum dictated this cosmic pirouette, flattening the cloud into a disk. At the center, where material was most densely packed, temperatures soared as gravitational potential energy converted to heat. This central region would become our Sun. The disk wasn't uniform. Closer to the forming star, temperatures reached thousands of degrees Celsius, vaporizing everything except the most refractory materials, metals, and rocky minerals. Further out, beyond what we now call the frost line, temperatures dropped low enough for water, methane, and ammonia to freeze into solid ice. This temperature gradient would fundamentally shape the architecture of our solar system. Within the disk, tiny dust grains began to stick together through electrostatic forces. These microscopic collisions built larger and larger aggregates, from dust bunnies to pebbles, from pebbles to boulders. The process was slow at first, but as objects grew larger, their gravity helped them sweep up more material. This was planetary accretion, the gentle phase of planet building. 4.5 billion years ago, the center of our solar nebula reached a critical threshold. The core temperature climbed to 10 million degrees Celsius, hot enough to fuse hydrogen nuclei into helium. Nuclear fusion ignited, and our Sun was born in a blaze of thermonuclear glory. The young Sun was different from the star we know today. It was about 30% dimmer, but far more active. Powerful stellar winds streamed from its surface, carrying away much of the remaining gas in the inner solar system. These T-Tauri winds, named after a class of young, variable stars, would play a crucial role in clearing the cosmic construction site. The Sun's ignition sent shockwaves through the surrounding disk. The stellar wind created a cavity around the newborn star, pushing gas and fine dust outward. Only the larger, more massive objects, the planetary embryos that had already begun forming, could resist this cosmic gale. During its first 100 million years, the Sun was a turbulent, unstable star. Solar flares erupted from its surface with devastating intensity, bombarding the inner solar system with high-energy particles. The magnetic field of our young star was chaotic and powerful, creating vast loops of plasma that extended millions of kilometers into space. This early solar activity had profound implications for the developing planets. The intense radiation and particle bombardment stripped away any early atmospheres that the inner planets might have accumulated. Only later, through volcanic outgassing and impacts from volatile-rich comets and asteroids, would these worlds acquire the atmospheres we observe today. In the hot inner regions of the solar nebula, within about 4 astronomical units of the Sun, only refractory materials could condense from the gas. Silicon combined with oxygen to form silicate minerals. Iron and nickel formed metallic alloys. These materials accumulated into countless planetesimals, asteroid-sized bodies ranging from kilometers to hundreds of kilometers across. The terrestrial planets, Mercury, Venus, Earth, and Mars, formed through the collision and merger of these rocky planetesimals. But this was no gentle process. As objects grew larger and their gravitational pull increased, collisions became increasingly violent. The energy released in these impacts was tremendous, heating the growing planets to molten states. Mercury, closest to the Sun, faced the most extreme conditions. The intense solar radiation and powerful stellar winds stripped away most of its lighter elements, leaving behind a world that is primarily an iron core with only a thin, rocky mantle. This small planet, barely larger than Earth's moon, bears the scars of countless impacts and the extreme thermal stresses of orbiting so close to our star. Venus formed under more moderate conditions but evolved into a hellish world. Its similar size to Earth meant it retained heat efficiently, but its proximity to the Sun triggered a runaway greenhouse effect. Water vapor in its early atmosphere trapped heat, which created more water vapor, which trapped more heat. Eventually, all surface water evaporated, leaving behind a dense atmosphere of carbon dioxide with surface temperatures hot enough to melt lead. Earth occupied the perfect position in what we now call the habitable zone. Not too hot, not too cold, but just right for liquid water to exist on its surface. Earth's formation was marked by a catastrophic event that would shape its future. A Mars-sized object called Theia collided with the young planet about 4.5 billion years ago. This giant impact ejected enormous amounts of material into orbit, which eventually coalesced to form the Moon. Mars, the outermost terrestrial planet, formed from less material than Earth and cooled more quickly due to its smaller size. Evidence suggests that early Mars had a thicker atmosphere and liquid water on its surface, carved into vast river valleys and lake beds. However, its weak magnetic field couldn't protect its atmosphere from the solar wind, and over billions of years, Mars lost most of its air to space, becoming the cold, dry desert we see today. Between Mars and Jupiter lies a region that tells one of the most fascinating stories in our solar system's history. The asteroid belt contains thousands of rocky objects, from tiny pebbles to Ceres, a dwarf planet nearly 1,000 kilometers in diameter. But this region was once destined to become another terrestrial planet. The gravitational influence of Jupiter, the solar system's giant, prevented the asteroids from accreting into a single world. Jupiter's massive gravity stirred up the orbital velocities of objects in this region, causing collisions to become destructive rather than constructive. Instead of sticking together to build a planet, rocky bodies shattered into fragments. The asteroid belt serves as a museum of the early solar system. These objects preserve materials from the solar nebula largely unchanged by geological processes. Some asteroids are metallic, composed primarily of iron and nickel, remnants of the cores of larger bodies that were disrupted by collisions. Others are rocky, made of silicate minerals similar to terrestrial planet material. Still others are carbonaceous, containing organic compounds and water-bearing minerals that may have been crucial for the development of life on Earth. Ceres, the largest object in the asteroid belt, is particularly intriguing. This dwarf planet shows evidence of water ice beneath its surface and may even have a subsurface ocean. Bright spots on its surface, likely salt deposits, suggest that briny water has recently erupted through cracks in the icy crust. The asteroid belt continues to evolve today. Collisions between asteroids create new fragments and occasionally send meteoroids toward the inner solar system. These cosmic messengers, when they reach Earth as meteorites, provide us with direct samples of the early solar system, allowing scientists to study the conditions that existed during planet formation. Beyond the frost line, where water could freeze into solid ice, the rules of planet formation changed dramatically. Here, in the outer reaches of the solar nebula, the most massive planets in our solar system were born. Jupiter and Saturn, the gas giants. Jupiter began forming much like the terrestrial planets through the accretion of solid planetesimals. But in the cold outer nebula, these building blocks included not just rock and metal, but also water ice, which was far more abundant. This allowed Jupiter's core to grow rapidly, reaching perhaps 10 to 15 Earth masses within a few million years. Once Jupiter's core became massive enough, something remarkable happened. Its gravity became strong enough to capture gas directly from the surrounding nebula. Hydrogen and helium, the most abundant elements in the solar system, fell onto the growing planet in a runaway process. Within perhaps a million years, Jupiter had accumulated a massive atmosphere over 300 times the mass of Earth. Saturn followed a similar path, but formed slightly later or in a region with less material available. Its core triggered gas accretion, but by the time this happened, the solar nebula was already beginning to dissipate. As a result, Saturn is less massive than Jupiter and has a lower overall density, so low that it would float in water if there were an ocean large enough to contain it. Both gas giants profoundly influenced the architecture of the solar system. Jupiter, in particular, acted like a gravitational shepherd, its massive pull affecting the orbits of countless smaller objects. Computer simulations suggest that Jupiter may have migrated inward toward the Sun during its formation, then migrated back outward. This grand tack model helps explain why Mars is so much smaller than Earth and Venus. Jupiter's gravitational influence prevented Mars from accumulating as much material during its formation. The gas giants also became the centers of their own miniature solar systems. Their powerful gravity captured numerous moons, some of which are among the most interesting worlds in our solar system. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, were discovered by Galileo in 1610 and revolutionized our understanding of the cosmos. Saturn's largest moon, Titan, is larger than Mercury and has a thick atmosphere and lakes of liquid methane on its surface. In the frigid outer reaches of the solar nebula, beyond Saturn's orbit, 2 more giant planets formed. Uranus and Neptune, the ice giants. These worlds represent a different class of planet entirely, with compositions dominated by water, methane, and ammonia ices mixed with rock and metal. Uranus and Neptune likely formed closer to the Sun, in the region between Jupiter and Saturn, but were gravitationally scattered outward during the early dynamic evolution of the solar system. This migration explains several puzzling features of these distant worlds, including their tilted axes and unusual magnetic fields. Uranus is unique among the planets for rotating on its side, with an axial tilt of 98 degrees. This extreme orientation was likely caused by a collision with an Earth-sized object early in the solar system's history. The impact not only knocked Uranus over, but may have also contributed to its unusual magnetic field, which doesn't align with its rotational axis and appears to originate from its outer layers rather than its core. Neptune, the outermost major planet, is a world of extremes. Despite receiving only 1,000th the sunlight that Earth does, it radiates 2.6 times more energy than it receives from the Sun. This internal heat source drives the fastest winds in the solar system, with atmospheric speeds reaching up to 2,100 kilometers per hour. Both ice giants have fascinating moon systems. Uranus has 27 known moons, many of which appear to be captured asteroids or Kuiper belt objects. Its largest moon, Titania, shows evidence of past geological activity, with vast canyons cutting across its icy surface. Neptune's largest moon, Triton, is even more intriguing. This world orbits backward compared to Neptune's rotation, suggesting it was once a Kuiper belt object that was captured by the planet's gravity. Triton has active geysers that spew nitrogen gas and dark particles, high into its thin atmosphere. Beyond Neptune lies a vast region of the solar system that remained largely mysterious until the late 20th century. The Kuiper belt, stretching from about 30 to 50 astronomical units from the Sun, contains thousands of icy objects left over from the solar system's formation. These pristine remnants preserve conditions from the outer solar nebula largely unchanged over billions of years. The Kuiper belt is home to several dwarf planets, including Pluto, once considered the ninth planet in our solar system. Pluto, discovered in 1930, reigned as the smallest and most distant planet for 76 years until the International Astronomical Union reclassified it in 2006. This decision wasn't arbitrary, it reflected our growing understanding that Pluto is just one of many similar objects in the outer solar system. Eris, discovered in 2005, is more massive than Pluto and helped trigger the reclassification of what constitutes a planet. Other dwarf planets in this region include Makemake and Haumea, each with unique characteristics. Haumea, for instance, rotates so rapidly that it's stretched into an elongated shape, and it has two small moons and a ring system. Beyond the classical Kuiper belt lies the scattered disk, populated by objects with highly elliptical orbits that were gravitationally scattered by Neptune during the early solar system's dynamic evolution. The most famous scattered disk object is Sedna, which follows such an extreme orbit that it takes over 11,000 years to complete one trip around the Sun. These outer solar system objects are crucial for understanding the early history of planetary formation. Many show evidence of past collisions, and their varied colors and compositions tell us about the chemical processes that occurred in the cold, outer regions of the solar nebula. Some, like Pluto's moon Charon, may have formed through giant impacts similar to the one that created Earth's moon. At the very edge of the Sun's gravitational influence, perhaps 50,000 to 100,000 astronomical units away, lies the Oort cloud, a vast spherical shell of icy objects that represents the final frontier of our solar system. Named after Dutch astronomer Jan Oort, who first proposed its existence in 1950, this region contains trillions of cometary nuclei in a deep freeze that has lasted since the solar system's birth. The Oort cloud objects formed much closer to the Sun, in the region of the giant planets, but were gravitationally scattered to these extreme distances during the early period of planetary migration. Here, barely bound by the Sun's gravity, they orbit in slow, stately paths that take millions of years to complete. Occasionally, the gravity of a passing star or the galactic tide nudges an Oort cloud object inward, beginning a journey toward the inner solar system that can take hundreds of thousands of years. These visitors become the long-period comets that grace our skies unpredictably, bringing with them pristine materials from the solar system's birth. The most famous of these visitors is Comet Hale-Bopp, which provided a spectacular display in 1997. Such comets offer us direct samples of the outer solar nebula, their ices and embedded dust grains preserving chemical fingerprints from 4.6 billion years ago. When these comets approach the Sun, solar heating sublimes their ices, creating the characteristic tails that can stretch millions of kilometers across space. The Oort cloud marks the practical boundary of our solar system, the region where the Sun's gravity gives way to the gravitational influence of neighboring stars. Beyond this lies interstellar space, where our solar system merges with the broader galaxy. About 4.1 to 3.8 billion years ago, the inner solar system experienced a cataclysmic period known as the Late Heavy Bombardment. Evidence for this event comes primarily from the Moon, whose heavily cratered highlands preserve a record of intense impact activity during this time. The surfaces of Mercury, Venus, Earth, and Mars all bear scars from this cosmic onslaught. The Late Heavy Bombardment may have been triggered by a period of orbital instability among the outer planets. Computer models suggest that Jupiter and Saturn passed through a 2-1 orbital resonance, causing gravitational chaos that scattered asteroids and comets throughout the solar system. Some of these objects were flung into the inner solar system, creating a spike in impact activity. This bombardment had profound implications for the early evolution of life on Earth. The intense impacts may have sterilized the planet's surface multiple times, forcing any early life into deep subsurface refuges. Paradoxically, the same impacts may have delivered water and organic compounds essential for life's emergence. The timing of the bombardment's end, around 3.8 billion years ago, coincides roughly with the earliest evidence for life on Earth. The Moon, lacking an atmosphere and geological activity to erase impact scars, serves as our best record of this violent period. The lunar highlands are saturated with craters from this era, while the younger, darker Maria lunar seas, formed when asteroid impacts created massive basins that were later filled with basaltic lava flows. Mars also preserves evidence of the Late Heavy Bombardment in its southern hemisphere, which is heavily cratered and much older than the smoother northern plains. Some of the largest impact basins in the solar system formed during this period, including the Hellish Basin on Mars and the South Polatecan Basin on the Moon. As the Late Heavy Bombardment waned, the planets settled into the more stable configurations we observe today, but their evolution was far from over. Each world followed its own unique evolutionary path, shaped by factors including size, distance from the Sun, composition, and the presence or absence of large moons. Earth's evolution was profoundly influenced by the presence of liquid water and the emergence of life. Early life forms began altering the planet's atmosphere, first through photosynthesis that added oxygen to the air. This great oxidation event, occurring around 2.4 billion years ago, was initially catastrophic for anaerobic life forms, but paved the way for more complex, oxygen-breathing organisms. The Earth-Moon system continued to evolve as well. Tidal forces gradually slowed Earth's rotation and pushed the Moon farther away. Early in Earth's history, days were only about 6 hours long, and the Moon appeared much larger in the sky. The Moon's stabilizing influence on Earth's axial tilt has been crucial for maintaining stable climate conditions that allowed complex life to evolve. Venus took a dramatically different path. Its dense carbon dioxide atmosphere created a runaway greenhouse effect that raised surface temperatures to over 460 degrees Celsius. Any water that might have existed on Venus's surface boiled away into space, leaving behind a hellish world shrouded in sulfuric acid clouds. Some evidence suggests that Venus may have been resurfaced by massive volcanic activity relatively recently in geological terms, perhaps within the last billion years. Mars lost its internal dynamo early in its history, causing its magnetic field to weaken and allowing the solar wind to slowly strip away its atmosphere. What was once a world with liquid water on its surface became increasingly cold and dry. However, Mars continues to show signs of geological activity, with dust storms that can engulf the entire planet and possible seasonal flows of briny water on steep slopes. The gas giants also continued to evolve, though more slowly than the terrestrial planets. Jupiter's Great Red Spot, a massive anticyclonic storm, has been raging for at least 400 years and possibly much longer. Saturn's spectacular ring system may be relatively young, perhaps formed from the disruption of a moon or large asteroid within the last few hundred million years. One of the most profound questions arising from our solar system's history is whether life exists elsewhere beyond Earth. The discovery of extremophile organisms on Earth, life forms that thrive in conditions once thought impossible, has expanded our understanding of where life might exist. Europa, Jupiter's ice-covered moon, has become a prime target in the search for extraterrestrial life. Beneath its frozen surface lies an ocean that may contain twice as much water as all of Earth's oceans combined. Tidal heating from Jupiter keeps this ocean liquid, and hydrothermal vents on the ocean floor could provide the energy and chemical gradients necessary for life. Enceladus, Saturn's small moon, has surprised scientists with active geysers that spew water vapor and ice particles from its south polar region. These geysers originate from a subsurface ocean, and chemical analysis of the ejected material has revealed organic compounds and conditions that could potentially support life. Mars remains the most likely place to find evidence of past life in our solar system. Ancient river valleys and lake beds suggest that Mars once had conditions suitable for life, and recent discoveries of organic compounds and seasonal methane variations in its atmosphere have fueled speculation about possible present-day microbial life. Even more exotic possibilities exist. Titan's hydrocarbon lakes might support entirely different forms of life based on methane rather than water. The subsurface oceans of other icy moons, including Ganymede and Callisto, could harbor microbial ecosystems. As our exploration of the solar system continues, each new discovery expands the realm of possibility for finding life beyond Earth. The solar system continues to evolve today, though at a much more sedate pace than during its violent youth. The sun steadily brightens as it ages, increasing in luminosity by about 1% every 100 million years. This gradual brightening will eventually make Earth uninhabitable, but that won't happen for another billion years or so. Asteroid and comet impacts continue to shape planetary surfaces, though at a much reduced rate compared to the early bombardment periods. The Chicxulub impact that helped end the age of dinosaurs 66 million years ago demonstrates that large impacts still occur and can have profound effects on planetary evolution. The outer planets continue their gravitational dance, occasionally perturbing the orbits of asteroids and comets. Neptune's gravity continues to sculpt the Kuiper belt, maintaining orbital resonances that create gaps and concentrations of objects. Some Kuiper belt objects follow orbits that bring them into the realm of the planets, where they may eventually impact one of the inner worlds or be ejected from the solar system entirely. Planetary rings continue to evolve as well. Saturn's rings are constantly changing as particles collide, merge, and are perturbed by the gravitational influence of the planet's many moons. Some scientists believe Saturn's rings may disappear entirely within the next 100 million years, their particles either falling into the planet or being scattered into space. The moons of the outer planets remain geologically active. Io's volcanoes continue to reshape its surface, driven by tidal heating from Jupiter. Europa's ice shell may occasionally rupture, allowing water from the subsurface ocean to reach the surface where it freezes into new terrain. These ongoing processes ensure that our solar system remains a dynamic, evolving system. Looking toward the future, our solar system faces dramatic changes on timescales that dwarf human history. In about 1 billion years, the sun's increasing brightness will trigger a runaway greenhouse effect on Earth, boiling away the oceans and making our planet uninhabitable. Life on Earth will need to adapt, migrate, or face extinction. In about 5 billion years, the sun will exhaust the hydrogen fuel in its core and begin fusing helium. This will cause the sun to expand into a red giant star, possibly engulfing Mercury and Venus. Earth, if it survives, will be a scorched, airless rock. The outer planets will receive more warmth, potentially making some of their moons temporarily habitable. Eventually, the sun will shed its outer layers, creating a planetary nebula and leaving behind a white dwarf star about the size of Earth, but with half the sun's mass. The planets will continue to orbit this stellar remnant, but they will be frozen worlds in perpetual darkness. On even longer timescales, gravitational interactions will gradually destabilize planetary orbits. Computer simulations suggest that within a few billion years after the sun's death, the planets may be scattered from their orbits, some falling into the white dwarf sun, others ejected into interstellar space to wander the galaxy as lonely rogue planets. The asteroid belt and Kuiper belt will gradually empty as objects are perturbed into the inner solar system or ejected entirely. The Oort cloud, weakly bound by the sun's diminished gravity, will be completely dispersed by passing stars within a few billion years. Our exploration of the solar system has revealed that planet formation is a messy, chaotic process that can produce an incredible diversity of worlds. Each planet and moon tells a unique story of formation and evolution, shaped by subtle differences in initial conditions and subsequent history. The terrestrial planets demonstrate how small changes can lead to vastly different outcomes. Venus and Earth formed under similar conditions but followed divergent evolutionary paths. Mars began with promise but lost its atmosphere and became a frozen desert. Mercury was stripped of its outer layers by the young sun's intense radiation. The gas giants show us that massive planets can form rapidly when conditions are right, but their final characteristics depend critically on the timing of their formation relative to the dispersal of the solar nebula. Jupiter's early formation allowed it to capture a massive atmosphere, while Neptune's later formation or more distant location resulted in a very different composition. The diverse moons of the outer planets have taught us that small worlds can be geologically active and potentially habitable if they have the right energy sources. Tidal heating, radioactive decay, and chemical energy can all drive geological processes that create conditions potentially suitable for life. The small bodies, asteroids, comets, and Kuiper belt objects preserve the raw materials and conditions of the early solar system. They serve as time capsules, allowing us to study the solar nebula's composition and the processes that operated during planet formation. The discovery of thousands of exoplanets, planets orbiting other stars, has revolutionized our understanding of planet formation and put our solar system in cosmic context. We now know that planetary systems are common in the galaxy, but our solar system appears to be somewhat unusual in its architecture. Many exoplanetary systems contain hot Jupiters, gas giant planets orbiting very close to their stars. These worlds likely formed farther out and migrated inward, a process that can be highly destructive to inner rocky planets. Our solar system appears to have avoided such dramatic migration, possibly because Jupiter migrated inward early but then reversed course and moved back outward. The abundance of super-Earths, planets larger than Earth but smaller than Neptune, in other systems highlights the gap in our solar system between Earth and the ice giants. Why didn't a super-Earth form in our system? The answer may lie in Jupiter's early formation and migration, which could have prevented such a world from accumulating sufficient material. Some exoplanetary systems are much more compact than ours, with multiple planets orbiting closer to their star than Mercury orbits the Sun. Others have planets on highly eccentric orbits, unlike the nearly circular orbits in our solar system. These discoveries have shown us that our solar system, while not unique, represents just one possible outcome of the planet formation process. The search for potentially habitable exoplanets has also refined our understanding of habitability. The concept of the habitable zone, the range of distances from a star where liquid water can exist on a planet's surface, has been expanded to include subsurface oceans on icy moons. This dramatically increases the number of potentially habitable worlds in the galaxy. Our journey through the history of the solar system reveals a story of incredible complexity and beauty. From the collapse of a primordial gas cloud to the emergence of life on Earth, each chapter in this cosmic saga demonstrates the profound interplay between chance and physical law that shapes the universe. The solar system is both our home and our laboratory for understanding planetary processes throughout the galaxy.